when we're reviewing, yeah. No.
After the exam. We're done. We're watching movies.
Yeah.
I'm feeling cheated out of learning.
Lesson 7.2, day 1. All right, this warm-up we're going to kind of do together. It's been a while since we've got to do some notes together. And I could use a little warm-up today, too. So we have R is this region that's bounded by 2 graphs. Y equals a natural log of X. That'd be this curve right here. And the line Y equals X minus 2. Okay, so we have this region that's shaded in gray. It says, though you may use a calculator, and we're going to want to, show the interval that you found to arrive at your answer. All right. Number 1 says, find the coordinates at which the 2 graphs intersect each other. So we're going to have to find these points. And that's going to help us set up our integral. And then we'll find the area. Okay, so to find where those intersect, we want to set these equations equal to each other. And since we can use our calculator for this, we're going to not try to solve this algebraically. We're just going to use our calculator. So, of course, I don't have that to look at. Okay. So let's type in, let's see what I did for colors here. I don't know X is blue. Okay, so we got our natural log of X. And that was X minus 2, right? Okay. All right, so there's my curves. So to find those points of intersection, we're going to go second calc. Where do these intersect? So 5. It's going to ask you first curve, so I'm probably going to start with this left bound over here first. First curve, get close to that point. Second curve, and it'll guess it for you. Okay, here we don't get an exact value, and we're just going to store this number in our calculator. So we can write this as one of our intersection points. X equals 0.1585, ... And then if you quit out of the graphing screen, so second quit, we want to do alpha X. And we want to store that value as, let's just do A. Alpha A. Okay, it's not stored in our calculator under our A value. And what you can do, and you can do this on the AP exam too on FRQs, is you can write a little A underneath there, and then you can actually use A instead of the number when you go to set up the integral, which we'll do in a second. All right, let's find that second intersection point next. Everybody good with storing?
How did you do that again?
The store. Yeah. So first you got to hit alpha and then X. And if you want to, you can hit enter just to make sure it has the right number in there. You're like, okay, yep, that was that value we got. And then you hit this one, the STO arrow. Store that as alpha A. And then just hit enter and your calculator will put that in its memory. Now it's stored in A. All right, we're going to do the same thing for the next one. Intersect. Number 5. First curve. Second curve. Yep. So now your calculator will have this one in. Are you talking about for this one? Oh, for the first one. Okay, well now mine's gonna not have that X value anymore. But alpha X is right here. And then you just want to store it as something else.
How do you get the number
It'll take it from there. It'll take it from your intersection point. It should take it. Yeah.
If you just hit X, you don't have to hit L.
If you just hit this one,
Yeah.
you can use that button. Okay, you could also just hit this one.
Well, even if you hit alpha on that one, it just pulls up the X.
On this one?
Yeah. I was doing it wrong. I didn't realize the X is way down there.
Oh. Okay. So now get that second one in there, and we're going to do the same thing. So let's do what Mark says. You don't have to hit alpha, just hit this button right here, X. And then just store that. Let's store this one as B. And again, it should feed you that number. Okay, so it's our second intersection point. We're going to call that B. So what else is that? So 3.1461. And then we could write a B underneath. Okay, so it says, although you may use your calculator to evaluate this, which we're going to have to with these non-exact intersection points, still set up the integral. So to find that area of our region R. All right, so here, am I going to want to do, well, obviously I kind of gave this away because we found the X values of point intersections, but again, if it helps you to draw on like a little rectangle, we're going to want to do this with respect to X. So to find this area, we're going to integrate. And then here, you don't have to put in the numbers. You can just say from A to B. And even on the AP exam, like the readers see that you called those A to B, so you can just write it in just like that. And to find the height of that rectangle, it would be the top curve, which is the ln of X, minus the bottom curve, which we graph these in parentheses, which is X minus 2. And then the width of this rectangle we call dx. And then honestly, that's all you have to show. And then you can just show the answer, which you're going to do in our calculator. I wouldn't even go any further. Don't even distribute like negative here or anything like that. You just have to set up the integral and then let your calculator do the work. So we're going to do math 9. And here's we're going to use alpha A as our bounds, alpha B. And this is more exact than just typing in those decimals too, because it uses that exact value that we got for that point of intersection. And then we're going to do our top minus our bottom, which we have those stored in our y1 and y2. So y1 minus y2. You don't even have to retype the functions. Dx. This was an old AP exam problem. I stole this one. I think it was a 2012. This is just obviously part 1. This was worth 3 points though. 3 of the 9, which is the first part. I think it was.
We don't need a unit on that.
Nope. Yeah, no units on here. The only time you need units are like applied problems. I think it was 1 point for finding the correct points of intersections and having the right bounds. 1 point of setting up the integral correctly, and 1 point for having the right answer.
If you put A and B, they're fine. You can put it.
As long as you write it in your work next to the values. Yeah. If you weren't to do this, then you would lose points. Because then they don't know that you stored those as A and B. And they don't know which one's which. Yeah. So you just have to label for them. If you're nervous about it, you can always write in the numbers too with the ... but that's more work. Okay, so as a reviewer 7.1. So now we're getting into volume. Okay, so I mentioned this before to you guys of how we're basically just going to take like little area regions, which we've been practicing in 7.1, and we're just going to take them and rotate them about a line, sometimes an axis, sometimes just like a line like y equals 1 or something like that. And they're going to form solids. We call these solids of revolution. All right, I found a couple YouTube clips of just like some nice visuals. So I'm going to play the first one here. Oops, you can see I started watching it. Oh gosh, not take it away. Okay. We don't really need the sound. So here they just kind of go through, it's like an animation. The square root of x. And then they give you like this line. I think it has like a really, not a very steep slope, really flat, 1/10 right there. And then they take that region in between those two curves. Oh, just kidding, x equals 4. We're going to cut it off there too. There's the region. And then they're going to rotate this. Oh, look at this 3D. Around the x-axis, and you can see how we have a solid being formed. So this one, you can see there's like a hole in the middle. So they're showing you right there. This is what we call like a washer, you know, like those tool things that are washers, like that. So we'll calculate basically finding like the volume of one of those, and then we just integrate it, which adds up the volume of all those like different slices. So that one was a washer. So we basically learned two methods. One's called a disc and one's called a washer. Okay, let's look at this one. This one's a little bit longer. We don't have to watch the whole thing, but I kind of like this one because they show you step by step. So this time we're rotating this region around. This time it's going to form a disc because there's no like hole in the middle because this region is being rotated around the x-axis. So this is what we call a disc. And essentially, you know, obviously this has to do with like an area of a circle, make it 3D, times it by the width to make it volume. And then we just integrate it to add up all these. This one, another disc, but this time we're rotating about the y-axis. So sometimes that can happen where we do this with respect to y. Okay, you can see here again our solid. If I were to just like take like a slice out of it, this one would be like a disc because there's no hole again. Okay, they're kind of showing you too like a little slice we're taking there. And that's another reason why I kind of like to have you draw rectangles in when we do the areas, because it kind of helps with when you get to volume. Here's an example rotating about the x-axis, and this is one where it's going to form a washer. Again, you can see there's a hole here, and they're kind of showing as the washer. You take like little snapshots of the wash, you can see that hole in the middle. Okay, so then we just calculate the area of one of these. Volume is width, integrate it to add up. It's basically what we're doing. Ooh, look at that. Another washer. So those are the only two methods you need to know in AP. It's called the washer method and the disc method. There's something called the shell method, but you don't need to know that for the AP exam, so we're not going to do it. That's pretty much all we have left to learn. So like just getting like the conceptual stuff down, I think is obviously important, but once you get to the calculus part, if you're strong with like integrals and if you understood 7.1 really well, it's not that much harder. It's just like adding on an extra step of now we're doing volume instead of just area. Okay, kind of get the idea? How to see it? All right, so let's start off simple. So as I mentioned, it's either going to form two shapes, something we call a disc or something that looks like a washer. So when you don't have any gaps between the area that the region that you're rotating and the axis that you're rotating around. So look at this one, even though it's kind of a funky curve, for rotating this one around the x-axis this way. You can see there's no gaps between the region and where I'm rotating this axis here. So if I look at what it's forming, it's going to form like a closed disc is what we call that. So how do you find the area of this disc or of this circle? You do pi r squared, where this right here would be the radius from like the top to what I'm rotating around. That would be like my radius. So basically just find the area of the circle, pi r squared, and then to make this 3D, we times it by dx, but we'll get to that. Okay, the other region that could form is if we do have like a gap. So here you can see we're rotating this one about the x-axis too. But I kind of have like this gap right here. And so when I rotate it, I have this hole in the middle of my solid. Okay, so we call this a washer. So how we find the area of this washer is we take the area of the big circle, like the area of this big one. So what we do is we call that like our big R, our big radius. That'd be like from here to here. Would be our big radius. And then we subtract out the area of this little circle, the inside, to find this area. So then that would be like this little, we call that little r. This little radius right here. So what I like to do to kind of just get like a visual, we're still going to sketch the region. So it's like the first thing you do. just like when we did area. We're going to sketch the region, and then we're going to label which axis we're rotating around. All right, so if this is my problem here, I would start by sketching this curve and then drawing in where am I going to rotate it. Then I like to draw like a little rectangle, and I picture taking that little rectangle and rotating about whatever my axis of rotation is. And I ask myself, okay, is this going to be a disc or is this going to be a washer? And in this case, since there's no gap, that's going to form a disc. So then I have to identify and label what the radius is. Okay, so in this case, I'm like, all right, if I picture taking this, revolving it around the x-axis, this right here would be my radius. Here's an important connection. I wrote this in your notes for you. And the reason why I say radii is because if we have a washer, we're going to have two radii that we have to pay attention to, like that big R and that little r, because when we go to find the area, we're going to have to subtract out that hole in the middle. Okay. This is the key point that I put in your notes. Your radii should always be perpendicular to whatever axis you're rotating it around. Okay. And that will also help you identify if you're going to do it with respect to x or with respect to y. All right, so if you have, for example, the x-axis, a horizontal line that you're rotating around, your radii should be vertical. Okay. If we're going to rotate it around the y-axis, then our radii should be horizontal. All right, then we basically just set up our integral. So we're going to write the volume in terms of the appropriate variable. Don't write dp here. I don't really like that. Write the volume in terms of the appropriate variable. So whether we're doing that with respect to x or with respect to y. And then we'll find the limits, and we're just going to integrate it to find the volume. So here's kind of like I don't really call it a proof, but just like a little bit of the algebra. Let's say we have a washer here that I kind of like to show students. So to find the area, okay, let's look at this washer right here. Pretend this is just a flat washer, which again, you can sketch like a little rectangle here. Here's my area, here's my region. I have a little rectangle rotating about the x-axis, and I can see this is going to form a washer because I have a gap here. Where this distance right here is my big radius, this little distance is my little radius. So to find the area of just one of these washers, I take the area of the big circle, which is pi big radius squared minus pi. Now I'm going to subtract out that little green region, little radius squared. So what we do is we factor out that pi, so you can see that right here. Okay, that would be if I was just to find the area of like that slice I took, that washer. So to find volume, think about how you find the volume of like any like shape or like any like polyhedron. You take the area of the base times the height, right? So to find the volume, I'm going to take the area, and now I'm just going to make this three-dimensional by timesing by the width, which we call dx. And that's basically our big idea here. Where the dx is like the width of one piece. And to add up, basically, every single disc or washer, whatever our slice is, we integrate it between our limits and our bounds. Okay, we're going to start with the disc method. That one's a little bit easier when you don't have to worry about having two different radii. We'll see how far we get today, but we'll start with the disc method. So obviously there's kind of like two different setups, and it depends on our curve and it depends on which axis we're rotating around. And if I have something that looks like this, and similar to like when we're doing area, if I have like a top minus bottom type of situation here, I'm going to do it with respect to x. Okay, and remember, you should always be taking your radii or kind of like your slice perpendicular to what you're rotating around. This is if I have a horizontal axis of revolution. If I have a vertical axis, we're going to do it with respect to y. So you can see the only difference there is our variables are with respect to y. And again, that was one thing. Make sure you're in terms of the appropriate variable for what we're finding the volume of. Okay. And then again, where this like formula comes from, here's the area of the disk times dx. We're making it three-dimensional times the width. And then we're just summing up all of the disks in between A and B by using limits. Or not using limits, by using integrals. That would suck to have to do these with limits. Okay, let's try one. So for the first like 4 in our notes, I screenshotted what the solid would look like just to give you a visual, but you obviously will not be given this picture. Okay, this is like what you have to picture in your head. So it says, find the volume of the solid formed by revolving the region bounded by the graph. F of x equals the square root of the sine of x about the x-axis. Okay, so you probably don't know what the square root of sine of x looks like off the top of our head. We could make a table, but we could also use our graphing calculator to make this quicker. So let's go ahead. Y equals the square root of the sine of x. Let's just get a little visual here. I'm like, okay, I didn't even change my windows from previous. There's what my region looks like. So I always start by sketching the region and labeling which axis we're rotating around. Okay, so the region looks something like this. And I might not know exactly where this intersects the x-axis, but how I could find that is I could figure out where is my curve at my points of intersection. Technically, when it intersects the x-axis, one is this 0. Square both sides. We get the one is the sine of x equal to 0. Okay, I'm thinking on my unit circle. One is sine 0. That would be at 0. Oh. Okay, well, get out of here. When x is 0 and pi. So that makes sense that this right here would be 0 and pi. If you want to, you can shade in the region. I usually don't for these ones because I like to differentiate it of like, I'm not trying to find the area of the region. I am trying to revolve that region about the x-axis. And I like to do this. I like to label which axis I'm revolving around. Okay. After I get this region in the sketch down, then I have to identify and label what my radius would be. So here's where I like to draw a little sliver. I'll do it. I'll just do it here. I draw a little sliver, and this sliver should always be perpendicular to the axis that you're revolving around. And I picture taking this little chunk and revolving it, so like you can literally like picture here, taking this and like revolving it around the x-axis, and I'm going to have a solid disc that's formed, right? There's no gaps or anything like that. I literally picture taking this. Here we go. Sorry for people on the video. I feel like this is hard to do over video. This, and I'm just revolving it around like that. It's going to form a disc, okay? So my radius of one of these discs, and obviously I gave you the screenshot of what the solid looks like. My radius would be this distance right here. And I always label my radius. Kind of like the step thing I do. I don't need to have, there's no big R or little r in this case because I have a disc. All right. Now I think we're ready to write the volume. So basically, the volume of one of these discs would be, I'm going to write it kind of weird, pi r squared. Okay, let's just use this round. Pi r squared would be the area times, to make this three-dimensional, the width of this is dx. That would be the volume of one of those discs. Okay. So to find the volume of the entire solid, I'm just going to add up an infinite number of disks between 0 and pi. So how you do that is using integrals. All right, since pi is a constant, you'll typically see it written outside of the integral, brought out, because that makes your algebra easier too when you actually have to go to find the antiderivatives. My bounds of my region here would be 0 to pi. r squared, how you find the length of the radius is very similar to how you'd find the length of like the height of the rectangles when you're doing areas. In this case, I got to do top minus bottom. So it would be the square root of the sine of x minus 0. So I'm not going to write in that minus 0 there. That, and then don't forget you have that squared, radius squared, and then dx. Okay, everybody good with that? Makes sense? All right, then from here it's just calculus. So again, I'm going to have you guys do the same thing as what I was doing with the area. Take it to the point of doing the antiderivative. So here, those would cancel. Antiderivative of sine is negative cosine. So take it to this point. You don't have to show the fundamental theorem of calculus. You can if you want. This one's not too hard to do because you just have to plug in pi and 0. But I do want to see your final answer. All right, I'll just do this one and then I won't do the one. So cosine of pi plus cosine of 0 minus negative. So let's see, that'd be pi. Cosine of pi is negative 1, so it'd be 1. Cosine of 0 is 1. So we end up getting 2 pi. So a lot of times, the answers to these you want to leave in terms of pi. Okay, that's like our exact answer. Obviously, if you go to check this in your calculator, which I'm going to do in a second here, it's not going to give it to you in terms of pi. Okay, just like when you solved trig equations in pre-calc, you had to do that by hand. But you can check, obviously, by doing 2 times what pi is and see if you get what that decimal is. So 2 times pi is like 6.2318, ... This is how you should write your answer in terms of pi. Well, let's go ahead, and this is what you would type into your graphing calculator right here. And I already have that square root of sine of x in my y1. Okay, so to calculate the volume, I would do pi, math 9, from 0 to pi, my radius, which was my y1 minus 0, because it's tucked up right on the x-axis, squared with respect to x. And let's see if we get about whatever 2 times pi is. I'm like, oh yeah, 2 times pi is the exact same as that decimal. Okay, that's about as easy as they get. Ones like that where they're nice tucked up against the x-axis. You have this nice disk that's formed. Pretty easy one to anti-derive. Good fundamental theorem of calculus. But again, I'm okay on your homework. We're going here to here. I'm like just doing it in your calculator. There to the exact answer. Okay. Any questions so far? Was that fun for you guys?
So then, if you did it without like doing the rest of that, like showing that work,
Yeah.
wouldn't you just get the decimal then?
Well, see, that's what I'm saying is like in your calculator. Oh, I see what you're saying. Yeah, you would. I see what you're saying. Because if you like type that in your calculator, well, I mean, you could type like this piece in your calculator. You know, in the end, you just have to times it by pi. Does that make sense? So when you're doing these, like you can do this part, the fundamental theorem part of calculus in your calculator, and then in the end, you're just going to have to tuck pi into your answer. So even if like you evaluated this and you get like 2/3, then it'd be 2 pi over 3 as your final answer, because that pi will always be out here.
So don't put the pi first. Just know that you have to multiply pi in at the end.
Right. Like I would do the fundamental theorem of calculus. Just like with any constant, I usually do that. I kind of like leave it out. Evaluate this first and then multiply that in. I mean, you like could, it would just make it probably a little bit more complicated. Okay, let's try another one. So this time we're not gonna revolve it around the x-axis. We're gonna revolve it around the line y equals 1. Okay, so again, I like jumped ahead and gave you the solid, but we wouldn't normally get this picture. We would have to sketch the area here. So I have a parabola that's shifted up to, and it's a sad face parabola. I have the line y equals 1. Go ahead and draw that in. And that's what I am rotating or revolving this around. Okay, now You can do the algebra if you want, but I think we all kind of know our shape of our parabola here. This would be the vertex. It would intersect there at 1 and -1. Yeah, you could always set these equal to each other. Oh, shoot, I meant to do that in green. 1 is that equal to 1. Do the algebra, you get positive -1. Okay, so there's those points of intersections. Okay, so there's my sketch. So it's tucked up right against my axis of rotation. So if I were to draw in my little slice here, and I picture rotating that about the line y = 1, you can see how this solid would be formed. Another disc. There's no holes, no gaps. Then I like to label the radius. So the radius would be this distance right here. Because again, I kind of pictured that rotating about the line y = 1. So you can see it wouldn't go any lower than 0. Here's like the radius. I labeled over there. Okay, so I have another disk. So to find the volume, pi, I'm going to write it out in front. I'm integrating this from -1 to 1. To find the area of one of the circles, I just have to do the radius squared. Okay, now this radius is a little different because it's not tucked up against the x-axis. So to find the length of that radius, I'm going to have to do my top curve minus my bottom curve. So 2 minus x squared minus 1. Okay, and this kind of stems off of what we talked about in 7.1. Now don't forget to square that because it's my radius squared. And then to make this volume 3-dimensional, times by the width dx. Okay, so again, that's kind of step 3. Write the volume, make sure you have in terms of the appropriate variable. So I'm doing this with respect to x. It's perpendicular to my axis of rotation, so everything's looking good here. All right, let's clean up this integral a little bit. So I wrote that -x squared first. 2 minus 1 is positive 1. I have -1 for some reason. Okay. Square that. So that's this algebra here. So it'd be positive x to the 4th, negative 2x squared plus 1.
Oh, I have -1.
I had -1 on this too. 2 minus 1 is positive 1. Isn't that funny? You can do all that calculus and the thing you do wrong is 2 minus 1. Okay, now I think we're ready to anti-derive. So this would be 1/5 x to the 5th minus 2/3 x cubed plus x. Okay, so as I mentioned, like this part, you could type in your calculator. Practice doing that and like practice being quick at that, because if you get your calculator on the AP exam, especially like a multiple choice type of situation where you don't have to show your work, you want to be fast, you want to be efficient at this. So if you type that in, you get 16/15. And then factor in the pi, so you have 16 pi over 15. Is that area? Obviously you can check this in your calculator and take 16 times pi divided by 15 and go get that decimal. Okay. I got time for one more. Oh, well. This is a good stopping point because I'm going to look at some washers. Let me just talk through washers and then we'll call it a day. Okay, so obviously you kind of seen these. So this method can be extended now if we have like a hole in the middle. So if we take a region like this and rotate it about something like this. Now if I have a hole here and I rotate it this way, you can obviously, we're gonna have that gap in here. So this is called like the washer method. So the only thing that's different is now to find the volume of one of these washers, we're still gonna do pi times what we call the big R. You can see that's what they're calling right here. Pi R squared. So we take the area of the whole circle, and then we subtract out the area of the little guy. Nah, that's my brand new pen. Whoosh. Okay. Minus.
I thought the black one was new.
It is. These ones, see how this one's old. They have like black tips, the new ones. I got a bunch of new ones.
What has your old one? You broke them?
Yep.
Dropped them?
On Friday, I seriously dropped so many.
You were on Friday.
Oh yeah, sorry, Wednesday. Okay, that's the area. And then to find the volume times by the width, we're gonna call it dx. dx. So the only thing that's a little different with the washers is we factor out that pi, so it makes it easier to integrate. So we do pi, big R squared minus little r squared, and then dx is how we find the volume of the washer. Where big R is the radius, what we call like the outer radius, and little r is what we call like the inner radius. Okay. So again, here's just like kind of another example. And here's your washer method. There's like your formula. Just comes from the area, timing by dx to get the width, using integrals to add up an infinite amount of washers. Okay, so this one is like our first washer one. We'll pick that up on tomorrow.
Should have printed me a color.
Oh, sorry, Jason. Want me to make a new one?
No.